Let's continue with the same example that we uh, left uh, that we were doing last time. Um, the example was 2u plus v plus w equals 5, 4u minus 6v equals minus 2, minus 2u plus 7v plus 2w equals 9. And we can write this in the equation form as 2, 4 minus 2, 1 minus 6, 7, 1, 0, 2, u, v, w equals 5 minus 2, 9. And if you recall, the three row operation that we did, so recall the three row operations were, first one was minus 2 row 1 plus row 2. Second one was row 1 plus row 3, row 1 plus row 3, and the third one was row 2 plus row 3. This implied E was 1, 0, 0, minus 2, 1, 0, 0, 0, 1. This implied F was 1, 0, 0, 0, 1, 0, 1, 0, 1. And this implied G was 1, 0, 0, 0, 1, 0, 0, 1, 1. And we said GFE into AX or into A equals U. This is the upper triangular matrix. And these are element matrices representing row operations. Elementary matrices representing row operations. And your G times F times E, if you recall from your last lecture, was 1, 0, 0, minus 2, 1, 0, minus 1, 1, 1. Also, G times F times E times B is some vector C, and C equals, so I can directly write C, where B is 5 minus 2, 9. So since B is 5 minus 2, 9, this implies C equals, so we pick one here, first one, then minus 2 times 5, which is minus 10, minus 2, minus 12, and minus 1 is minus 5, minus 5 minus 2 is minus 7, minus 7 plus 9 is 16. No, minus 1 into 5 is minus 5, minus 2, minus 7 plus 9 is 2. Okay, so this is C. Okay, and that's it, I think so. Okay, now how do we undo elimination? how do we undo elimination? Which means how do we reverse the elimination process? So first step was minus 2r1 plus r2. It was minus 2r1 plus r2, which implied E equals 1 0 0 minus 2 1 0 0 0 0 0 1 0 0 1. Okay. What if I do? What does 2r1 plus r2 give me? So 2r1 times r2 gives me 1 0 0 2 1 0 0 0 1. Okay. And what is this product? What is 1 0 0 2 1 0 0 0 1 times 1 0 0 minus 2 1 0 0 0 1? This is equal to first row 1 0 0. So because of this one I'm picking the first row, because of this one I'm picking the last row, and this means twice this row and 1 times this row. Okay, so 2 minus 2 is 0 0 1 0, and we have the identity matrix, which means this is E. Since this is E, this has to be E inverse. If this is E inverse, so this implies 2r1 plus r2 is indeed or does indeed. So 2r1 plus r2 does indeed reverse the elimination step. Does indeed reverses the elimination step. Okay, and this means what? So instead of minus 2, let me make this red just to emphasize. Instead of minus 2, I have a plus 1 here. So this minus 2 becomes a plus 1 if you want to reverse the elimination step, or so that is, so this means inverse of subtraction is addition. Inverse of subtraction is addition, or this means if Eij has minus L in ijth position, then E inverse Ij has plus L in the same position. Or GFE times A equals U, or A equals GFE inverse U, which is equal to E inverse F inverse G inverse times U, which is equal to LU. So this is the LU decomposition. And what is E inverse, F inverse, G inverse? So E inverse, F inverse, G inverse. So where E inverse, F inverse, G inverse is simply, so E inverse is 1 0 0 2 1 0 0, 0, 1. F inverse is 1, 0, 0. So we had 0, 1, 0. We had a 1 here, so we'll have a minus 1 here, 0, 1. And G inverse, is simply 1, 0, 0. 0, 1, 0, 0, minus 1, 1. So we can, so since multiplication is associative, we can multiply in any order. So let's multiply this one first. So I have 1, 0, 0, 2, 1, 0, 0, 0, 1 multiplied by, this is equal to, so this is again first row, 1, 0, 0. Pick the second row, 0, 1, 0, minus 1. So subtract the first row from third row. So this is minus 1, and 1. From multiply again, pick the first row, 1, 0, 0. Pick the last row here, minus 1, 1. And 2 times the first row, and 1 times the second row. So 2 times the first row is 2, 1, 0, 2, 1, 0, and this is a lower triangular matrix. This is a lower triangular matrix. This is equal to L. Or A equals L times U equals L, we know is 1, 0, 0, 2, 1, 0, minus 1, 1. So these are actually inverse. These are the inverse of the row operations. These are the inverse of the row operation. And U in our case was, if you recall, U in our case was 2, 1, 1. The first row was never changed. Where is 2, 1, 1? So it's 2, 1, 1. Then we had 0, 0 here, minus 8, minus 2, and then we had 0, 0, 1. So 0, minus 8, minus 2, 0, 0, 1. And if you multiply this out, this should give you, okay. So this is your lower, so you can always decompose this matrix into a lower triangular, and this is without a row exchange, and an upper triangular matrix. So a lower triangular and upper triangular matrix. So the first row is again 2, 1, 1. The second row is twice the first one, so it's 4, 4. This is 2, minus 8 is minus 6, and then it's 2 minus 2, which is 0. There's no contribution of the third row here. You subtract this first and second row from third row, so minus 2 here, 8, minus 1, 8, 7 here, and 2 and minus 1, 1 and 1, 2 here. So minus 2, 7, 2. And this is indeed the A matrix that we started working with. Okay. So to get directly L, all you need to do is negate the row operations here. So negate the row operations here, and you can write L directly. Let's see whether we can do that or not. So triangular factorization. So this section is on triangular factorization. With no row exchanges, A equals LU, where pivots are on the main diagonal, and A is ones on main diagonal. And the lower elements, and the elements below the main diagonal actually represent the row operations. Okay. Ones on main diagonal, and Lij taken from elimination steps. So let's do a couple of examples and then see whether we can write this or not. So example 1, A equals 1, 2, 3, 8, which I can directly write as L and U. So this is L, this is U. The first row will be the same, 1, 2. And what operation I am doing here? So to get rid of this 3, I want to do minus 3 R1 plus R2. So minus 3 means, so lower triangle, this is 1, this is 1, this is 0. So you can always write this directly. Then you need to get rid of this 3. So this rid of this 3 means this is minus 3. So you need to negate this. So this will be plus 3 here. And when you do this, this is 0, this is 8, and this is 2. So you need to calculate this value. You need to calculate this value. This can be directly written from this one. This you need to calculate. You need to calculate this one. And this is obviously 0. So if I multiply out, so 1 means first row, 1 and 2, good. And then 3 and 1 means you weight the first row by 3 and simply add the second row over here. And if you do that, so this is 3 plus 0 is 3, and this is 6 plus 2 is 8. So this is all right. What about another example? A is equal to 0, 2, 3, 4. You cannot be factored into LU since a row exchange is required. Since a row exchange is required, which is not a big deal. You can always multiply this by a permutation matrix. And so in general, PA is equal to LU. Okay. So A equals 1, 1, 1, 1, 2, 2, 1, 2, 3. This I can write in terms of L and U. L and U. So this is L, this is U. The first row is same. Here the first row is this one. Second row is this one. Third row is this one. Okay, so get rid of this one, get rid of this one. I need to do minus row 1 plus row 2. And I want to do minus row 1 plus row 3. Because of this minus here, this will become a plus here, and this will become a plus over here. Okay, and the only thing left is, so again, when we do this computation, minus row 1 plus, so this is 0, minus 1, 2, this is 1, and minus 1, 2, this is 1. Minus 1, 1, 0, minus 1, 2, this is 1. This is 1 here, and this is 2 here. So 1 here and 2 here. So this is 0. This is 0. And so when we do minus row 1 plus row 3, this will be 0. This is 0. This will be 1. This will be 2. So 1 and 2. So the third one, the third step I want to do is minus R2 plus R3. So when I do minus R2 plus R3, this will be 0, and this will be 1. And since because of this minus 1, this will be also plus 1. And if I multiply this out, what do I get? So 1, I pick the first row, which is 1, 1, 1. I add the first 2 rows, 1, 2, 2, 1, 2, 2. Then I add all 3 rows, so 1, 2, 3. Okay. So these are the pivots. These are the pivots. One's on the main diagonal, one's on the main diagonal, and these are row operations. Negative of row operations. This is negative of this one, and this is negative of this one. Okay. So inverse. These are the inverse operations. Inverse. Inverse. Another example. A equals 1 minus 1 0 0 minus 1 2 minus 1 0 0 0 0 minus 1 2 minus 1 0 0 minus 1 2. So this is a band matrix. If you look at here, this is a band matrix. So this is a band matrix. And probably this is also tuplets, where you have the difference between ij is the same when whether you are above the main diagonal or you are below the main diagonal. So this we can write as L and U. So again, L is 1 1 1 1 0 0 0 0 0 0, and again U is first row is as is 1 minus 1 0 0, and since this is upper triangular, this is 0, 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 and then this third row is also 0 over here. Okay, so to get rid of this minus 1, what I do is I do row 1 plus row 2. So row 1 plus row 2 simply means, so when I do the inverse of this one, this is a minus 1 over here. So when I do row 1 plus row 2, so 1 minus 1 is 0, 2 minus 1 is 1, so this is a 1 over here, and this is minus 1, this is 0, this is minus 1, this is 0. Good. So this comes from here, the inverse one. This is, so once I have 0, 1, minus 1, 0, so I can always then do row 2 plus row 3. When I do row 2 plus row 3, so row 2 plus row 3 means I will do a minus 1 over here. So because again, this is the negative or the inverse here. So row 2 plus row 3 would give me, row 2 plus row 3 gives me 1, and minus 1 will be 0. Minus 1 and 2 would be 1, and this will be minus 1. And finally, this one, so the last step would be, so this is a 1 and a minus 1, this is a minus 1 and a 2. So you will do row 3 plus row 4. Again, the inverse of row 3 plus row 4 simply means minus 1 here, minus 1 here, and this would be again 1. So if I multiply this out, so from with this one, I'll get the first row, which is 1 minus 1 minus 1 0. This one is, first row is subtracted from the second row. So minus 1 here, 2 here, minus 1 here, and 0 here. Then the second row is subtracted from the third row. So second row is subtracted from the third row. So 0, minus 1, 2, and minus 1. And then finally, the third row is subtracted from the fourth row. So 0, 0, minus 1, and 2. So you can directly write L and U. You can directly write L. Maybe you need some computations for U to write U, but you can directly write L from these row operations. Okay. If you look at this equation, so we have actually one linear system. We have one linear system, but two triangular systems equals two triangular systems. One is the lower triangular and the other is two triangular systems, is L and U, triangular systems. And we can easily solve this example. So which means AX, so since AX equals B, this implies LU times X equals B. This implies LC times L times C equals B, where U times X equals C. Is this all right? So this one is C, and we can always put a bracket here because it's complicated, it's associative. So L times, so we can first we can solve LC is equal to B. So solve this one first, and from here I can solve for X. So solve this first, solve this one first, this one first, and then solve this next. Solve this next. So let's do an example, and so probably it's much easier for you. So a good elimination code, because hopefully we want to write programs to solve these problems, and we don't want to do it by hand. Good elimination code will factor a into LU, and then solve for x from LU and B, Let's do an example, and probably this will be much more clearer. So same example as the last one. So we have this matrix 1 minus 1 0 0. We have x1 x2 x3 x4, and this is equal to B. B is 1 1 1 1. So this is B, this is x, and this is 0 minus 1. I'm sorry. This is minus 1 1 minus 1 2 minus 1 0. Then I have 0 minus 1 2 minus 1, and then 0 0 minus 1 2. Okay, good. And we know the LU for this one. So 1 minus 1 0 0, minus 1 2 minus 1, 0 minus 1 2 minus 1, and 0 0 minus 1 2. So this is the L, and this is the U. So let me write it in LU. So this is equal to L U. So L is 1 0 0 0, minus 1 1 0 0, 0 minus 1 1 0, 0 0 minus 1 1, and U was 1 minus 1 0 0, 0 minus 1, sorry, 0 plus 1, it's 1 on 1, 0 plus 1 minus 1 0, 0 0 1 minus 1, 0 0 0 1, right? So this is L, this is U, and multiplied by x1 x2 x3 x4 equals 1 1 1 1. Okay, so we say U into X is equal to C. Or maybe we say, so this is X. So we say U into X is equal to C. So this is some vector C. So C vector is actually C1, C2, C3, C4, right? And LC times B, now LC equals B, or this means C1 equals 1. C1 equals, so multiply this L by this C. So, and then we have minus C1 plus C2, minus C1 plus C2 equals 1. Then we have minus C2 plus C3, minus C2 plus C3 equals 1. And finally, we have minus C3 plus C4, and maybe I write it again, equals 1, equals 1, equals 1, equals 1. So now I can do forward substitution. If I do forward substitution, this implies C1 is equal to 1 and C2 is equal to, so C1 is equal to 1 from here. C1 is equal to 1, C2 is equal to, goes on this side, C2 is equal to 2, C3 is equal to, since C2 is equal to 2, so it goes on this side, C3 is equal to 3, and this goes on this side, and C4 is equal to 4. Good. So this is equal to 1, 2, 3, 4. Okay. And now we have U times X is equal to C. So now U times X equals C, which implies U is 1 minus 1, 0, 0, 0 minus 1, 1, 0, 1 minus 1, 0, 0, 0, 1 minus 1, 0, 0, 0, 1. This multiplied by x1, x2, x3, x4. This is equal to C, which is equal to 1, 2, 3, 4. Okay. So this is U. This is the unknown that we want to find, and this is C. So this equation gives us, now we'll do backward substitution because this one is x4 is equal to 4. So let me write here. So I'll write x1 minus x2 equals 2 plus x2 minus x3 equals, sorry, this one is 1. This is 1. This is 2. x3 minus x4, x3 minus x4 equals 3, and x4 equals 4. So now I do backward substitution, and this implies x4 equals 4, x3 equals, so x4 is equal to 4, so goes on this side, x3 is equal to 7, x2 is equal to, goes on this side, this is equal to 9, and x1 equals 9 plus 1, 10. So the solution of, AX equals B is X equals 10, 9, 7, 4. We can factor out. So from U, so we can make the pivots 1. So from U we can factor out a diagonal matrix D. And how do we do that? So if U equals D1, D2 up to Dn, this is all 0. Sorry, this is all 0. This is all 0. This is not, yes, U, and this is equal to 1. This is U12 divided by D1. This is U13 divided by D1, and so on and so forth. This is 0, this is 1, this is U23 divided by D2, and so on and so forth, and goes on. This is 0, goes on, this is 0, and finally this is 1. So now we have, this is a new U with 1s on main diagonal and pivots as elements on main diagonal here. So in general, A equals LU can be further simplified into A equals L du, where the new u has ones on main diagonal. Okay, good. So finally, what happens if we cannot do a row exchange? If we cannot do a row exchange, then you need to use permutation matrices. So row exchanges and permutation matrices. Permutation matrices. The first example, you have 0, 2, 3, 4 times uv equals b1, b2, b1, b2. This simply means 2v equals b1 and 3u plus 4v equals b2. I can reorder these, write these equations in any order. So what I do is, so if I multiply a permutation matrix here that exchanges the first and the second row, so this is the permutation matrix, that exchanges first and second rows into 0, 2, 3, 4 uv. Obviously, I have to multiply this one on this side here, 0, 1, 1, 0 times b1, b2. So this simply means this will do a row exchange, this will do a row exchange, this will not be changed, and we'll have 3, 4, 0, 2 uv as is. All we have done is I've written this equation here, and I have swapped these two equations, and obviously this will be swapped here too. So this is b2, b1. This is exactly the same set of equations. All we have done is we have done a row exchange so that we have pivots, and we can do Gaussian elimination. In fact, write this into an LB and a U. Okay, good. So when we do P times A times X, this is equal to P times B, and when we do this, so this is P times B, and this is P times A, and this X is still the same X. Nothing has changed. So mathematically, this is what we have done. This is what we have done. So we have multiplied a permutation matrix on both sides. Obviously, you need to multiply both sides, otherwise this equality is not going to hold. We already know what are permutation matrices. They have ones on any one row or column, and product of permutation matrices is also a permutation matrix. Is also a permutation matrix. Okay, and in general, there are n factorial permutations of size n. This implies if n is equal to 2, the two permutation matrices, the two permutation matrices are the identity and this one, the row exchange one. For n is equal to 3, this implies 3 factorial, which is equal to 6 combinations. 6 combinations, and those 6 combinations are, if I write this as 1 0 0 0 1 0 0 0 1, if I call this A, if I call this B, if I call this C, so I have A, B, C, then I'll have A, C, B, then I'll have B, A, C, then I'll have B, C, A, then I'll have C, A, B, and finally I'll have C, B, A. These are all the permutations. So A, C, B means 1, C, and B means this one. So note there is only 1 1 in each row or each column. 1 1. So B is 0 1 0, A is 1 0 0, C is 0 0 1, CBA is 0 0 1, B is 0 1 0, A is 1 0 0, CAB is 0 0 1, A is 1 0 0, B is 0 1 0, and B is 0 1 0, C is 0 0 1, and this is 1 0. So these are the 6 permutation matrices associated with n is equal to 3. A 0 in a pivot position, a 0 in a pivot position, in a pivot position may be easy, may be serious, or may be easy to fix, or may be easy to fix. Let's see. So you do that. So you decide. So how do you do that? You decide by looking below 0. You decide by looking below 0. If there is a non-zero entry, lower down in same column, then a row exchange is carried out. Let's see an example. You have A equals 0, A, B, 0, 0, C, D, E, F. If D equals 0, implies no first pivot, because these are already zeros. So if D is 0, then there is no first pivot. If A is equal to 0, then there is no second pivot. And if C is equal to 0, so if A is equal to 0, there is no second pivot. And if C is equal to 0, there is no third pivot. If D is equal to 0, the problem is incurable. Because it's a singular matrix, then is incurable, since A is singular, because there is a column of zeros, because A is singular, because column of zeros. So we know if there is a column of zeros, then the determinant is 0. If D is not equal to 0, if D is not equal to 0, you can exchange the first and the third row. Exchange first and third rows implies P31 equals, so what are first and third rows? 0, 0, 1. So second row remains as is, and the third row and the first row are changed. So if you do P31, you can do a row exchange. And if A is not equal to 0, if A is not equal to 0, then you can exchange second and third rows. Exchange second and third rows. And what is P23? This implies P23 equals, you are not going to change the first one. Second becomes the third, and third becomes the second. This is 0, 1, 0. Okay. So P23, P31 first, then P23, then A becomes, so 1, 0, 0, 0, 0, 1, 0, 1, 0 multiplied by 1, 0, 0. P31 is 0, 1, 0, 1, 0, 0. Sorry, 0, 0, 1. I'm sorry. 0, 0, 1. 0, 0, 1, 0, 1, 0, 1, 0, 0. And multiplied by A, which is 0AB, 0, 0, C, D, E, F. This will become what? So when we do first and third row exchange, when we do the first and the third row exchange, this becomes 0, 0, C remains there, D, E, F over here, and 0, A, B. And when we do the second and the third row, we'll have A, B over here, A, B over here, and we have 0 and C over here, and we have a matrix. So this is actually P times A, where this one equals P. Okay. So for non-singular matrices, so for non-singular matrices, a permutation matrix always exists. A permutation matrix always exists such that is normally written as this, such that P times A reorders rows of A, and a unique solution of X is possible. So for singular A, full set of pivots does not exist. Pivots does not exist. Does not exist. Does not exist, and this implies elimination fails. Elimination fails. Okay, good. So the second last topic, or the last topic in this chapter, or this is the second last topic, is inverses and transposes. Inverses and transposes. Not all matrices all matrices have an inverse, therefore trying to find x equals A inverse B is not a good option. Is not a good option. And why is that? So why won't matrices have an inverse? So matrices may not have an inverse. Matrices do not have an inverse. Matrices do not have an inverse. If the columns are not independent. And we've already looked at the definition of independence, and we will look at again when we go to the second and the third chapter. Also, a matrix cannot have two inverses. How do we prove that? So suppose B times A equals I. So since this is on the left of A, this is called a left inverse. This is a left inverse. And A times C equals I. This is on the right of A, so this is called a right inverse. So this is a left inverse, this is a right inverse. So the proof is, what is the proof? So the proof is B times AC, because this is identity, equals BA into C. Why? Because this is associative. But B times A is identity, or B times I is equal to I times C. So this is because of associative property. This equality is because of associative property. So B times I is equal to C, so this implies B equals C. Or the left inverse is equal to the right inverse. Okay. For a 2 by 2 matrix, you know this from high school. If A equals A, B, C, D, then this implies A inverse equals 1 over A. You swap these two, so this becomes D, this becomes A, and you negate these. So this becomes minus B, this becomes minus C, where A is AD. So the determinant is product along the main diagonal, and you subtract the product along the off diagonal, and this should not be equal to 0, because obviously you cannot divide by 0. Okay. And for a diagonal matrix, for a diagonal matrix, an inverse exists if none of the values, if none of the entries on the main diagonal is 0. And why is this the case? Because if A equals D1, D2 up to Dn, this is 0 here, this is 0 here, this implies A inverse is simply D1 inverse d2 inverse, dn inverse, and this is 0, where the determinant of A is simply the product. I is equal to 1 to n. This is the product sign of di's. And this is not equal to 0. Also, we have used this property before. Also, AB whole inverse is simply equal to B inverse A inverse. So order is reversed. Order is reversed. Order is reversed simply means, how do we prove this, that this is true? And this is also true for the transpose. So you need to memorize this one. The order is reversed. So the proof is AB times B inverse A inverse is simply B inverse into A inverse, which is equal to A into I into A inverse, which is equal to I, or B inverse into A inverse. The left and the right inverses. AB equals B inverse A inverse into A into B equals B inverse into I into B, which is equal to I. Similarly, ABC whole inverse is simply C inverse B inverse A inverse. Also holds for transpose. That is AB whole transpose equals B transpose A transpose. Okay. So how do we calculate an inverse? Although we don't want to ever calculate an inverse, how do we calculate an inverse? So calculation of A inverse by Gauss-Jordan method. This is nothing else but the extension of the row echelon form when your right hand side is an identity matrix. So how do you do calculation of A inverse by the Gauss-Jordan method? So let's look at this example. We have 2, 1, 1, 4, minus 6, 0. Same matrix, minus 2, 7, 2. And now I have, instead of 1, I have x1, I have x2, I have x3, and I say this is equal to E1, this is equal to E2, where E1, E2, E3 are unit vectors, just like I, J, and K, and this is some I3. So EI has a 1 in ith position, where EI has a 1 in ith position. Or what we have done is we have said, so this is A, this is some X. So we have said A times XI equals EI. So this is the extension of that equation. This is the extension. So this is the first column of AA inverse. This is the first column of AA inverse, and this is equal to unit vector or first column of I3, a 3 by 3 identity matrix. Now we have 3 different right-hand sides. We have 3 different right-hand sides. We have 3 different right-hand sides. So we have three different item size. We will do, so what we do is, so the procedure is proceed with row operations, row operations, until until an identity until an identity appears on the left hand side, side. So there's the Gauss-Jordan method. So let's do this one. So example is, so we have A here, we have E1, we have E2, we have E3, or this is equal to 2, 4, minus 2, 1, minus 6, 7, 1, 0, 2. This is 1, 0, 0, 0, 1, 0, 0, 0, 1. So the goal is to make this identity. Then this will be the inverse. Will be the inverse. Okay, so let's do that. We have actually already done this one many times. So so my operations would be minus 2R1 plus R2, R1 plus R3, and then we'll do the others later on. So this is 2, 1, 1. The first row will not change here. 1, 0, 0. So this will be 0. Minus 4 plus 4. Minus 2 minus 6 is minus 8. Minus 2 over here. Minus 2, 0 is minus 2. 1, 0. And then when I do plus, so this is 0. 7 plus 1 is 8. 2 plus 1 is 3. 1, 0, 1. 1, 0, 1. Then I'll do R2 plus R3, and R2 plus R3 will give me 2, 1, 1, 1, 0, 0, 0, minus 8, minus 2, minus 2, 1, 0, 0, 8 minus 8 is 0, 3 minus 2 is 1, 1 minus 2 is minus 1, 1 and 1, 1 and 1. Okay, so this, by the way, is U, and this, by the way, is GFE, which is equal to L inverse. You can check. Okay, so what do we want to do next is, I want to get rid of this one, and I want to get rid of this 2. So I say minus R3 plus R1. Now row 1 is going to change row 1, because this is coming later on, and then I do 2 times row 3 plus row 2. So this will become, so the last way is not going to change, minus 1, 1, 1. So minus R3 plus R1, so 2, 1, 0, 2, 1, 0, minus 1, 1 is 0, 1 and 1. Minus R3, so this is 2 minus 1 minus 1. This is 2 minus 1 minus 1. Okay, and when I do 2 row 3 plus row 2, so this is not going to change. 2 minus 2 is 0, and this is minus 2 is minus 4. 2 plus 1 is 3, and this is 2. So 2 minus 1, 1, minus 4, 3, 2, minus 1, 1. Now what I want to do is I want to get rid of this 8. So I say minus 1 over 8 R2. When I do that, so I simply divide the whole row 2 by minus 8. So 0, 0, 1, minus 1, 1, 1, 0, 1, 0. This is still 2, 1, 0. This is still 2, minus 1, minus 1. Minus 4 divided by minus 8 is half. 3 divided by minus 8 is minus 3 by 8. 2 divided by minus 8 is minus 1 by 4. And then what I do is I do minus, I get rid of this one. So I say minus R2 plus R1. So when I do that, so second and third rows are not going to change. 0, 0, 1, half, minus 3 by 8, minus 1 by 4, minus 1, 1, 1. This will become 2. Minus 1 plus 1 is 0. This is 0. And then this is 2 minus half is 3 by 2. Plus 3 by 8 minus 1. So plus 3 by 8 minus 1. Plus 3 by 8 minus 1 is minus 5 by 8. Minus 5 by 8. And this one would be plus 1 by 4 minus 1 is minus 3 by 4. Minus 3 by 4. And if I do the last step is R1 divided by 2. If I do this, so I'm getting rid of this 2. I'm making this 1. All I do is this one will become 1, 0, 0, 0, 1, 0, 0, 0, 1. This will become 3 by 4 minus 5 by 16 minus 3 by 8. This will be half minus 3 by 8 minus 1 by 4 minus 1, 1, 1. So you can go home. You can go home and say, so this is simply I, and this is A inverse. So this is A inverse, and this is I. You can go home and check. So at home, check A times A inverse equals A inverse times A equals I. So check this one. Okay, but again, just to remind you, computing A inverse, this is computing this, computing A inverse is not a wise idea. You should never try to compute A inverse. Okay, so transpose of a matrix is very simple. So transpose of a matrix, you convert, so A transpose is transpose of A, transpose of A, which implies you ith row of A, ith row of A becomes ith column, becomes ith column of A transpose. Okay, so for example, if A is equal to 2, 1, 4, 0, 0, 3, this implies A transpose is simply, so this is 2 by 3, so this would be 3 by 2, so 2, 1, 4, so this row becomes a column over here, and this row becomes a column over here, 0, 0, 3. This is transpose. So the only thing that you need to know for this transpose is AB whole transpose, just like the inverse, this is equal to B transpose, A transpose. And the most important property is this one, A inverse whole transpose. You can interchange these two, can interchange these two, which means this is equal to A transpose inverse. Okay. also A into A transpose whole transpose is equal to I transpose, which is equal to R. Diagonal matrix identity is its own transpose, but this one is equal to A inverse transpose into A transpose equals I. So you can always interchange this one. So this becomes A transpose inverse into A transpose. And obviously this is equal to I, because this is one matrix, this is the inverse of the other matrix, of the same matrix. And A transpose IJ equals AJ I. What are symmetric matrices? This is the last topic in this chapter. So the symmetric matrices, so symmetric matrices. So A is symmetric. A is symmetric if A equals A transpose. This simply implies off-diagonal elements are same. Off-diagonal elements are same. Or this implies Aij equals Aj. For example, A equals 1, 2, 2, 8. These are the same. And A transpose equals A, which is equal to 1, 2, 2, 8. The inverse of a symmetric matrix is also symmetric. And how do you prove that? Because A inverse whole transpose equals A transpose inverse, which is equal to A inverse. This, by the way, means because. And what are symmetric products? What are symmetric products? Symmetric products? Symmetric products are transpose R. For any rectangular matrix, R, R transpose R whole transpose equals R transpose, which is equal to R transpose R. So this means this is symmetric and square. By the way, symmetric matrices have to be square. And R times R transpose whole transpose is R transpose into R transpose is equal to R into R transpose. This is again symmetric and square. However, R transpose R is not equal to R transpose. Why? Take the example of R equals 1, 2. This implies R transpose equals 1, 2. This implies R transpose equals 1 plus 4. It's a 5 1 by 1 matrix here. This is a 2 by 1 here. This is a 1 by 2 here. So you get a 1 by 1 matrix. Also R transpose times R is 1, 2, 1, 2. This is 2 by 1. This is 1 by 2. So obviously this is a 2 by 2 matrix. Again, rank 1. So multiple of the first row, 1, 2, 2, 4, This is a rank 1 matrix. Rank 1 matrix. Okay. And what is the advantage gain for a matrix, for a symmetric matrix, when we do that for an LU decomposition? So the advantage is in terms of the number of computations. So if A equals A transpose, this implies A equals LDU, or this is equal to LDU transpose, which is equal to U transpose D transpose L transpose. Now D transpose equals D, because off diagonal elements are already 0. Off diagonal elements are 0, and elements on main diagonal are fixed. Main diagonal do not change. If this is the case, then this implies A equals LDU. So from here, A equals LDU equals U transpose D times L transpose, or U equals L transpose, or L is equal to U transpose. Or this implies A equals LDU is simply LDL transpose, if A equals A transpose. And a quick example for this one is A equals 1, 2, 2, 8. This is equal to L times U. So let me write L and U first. So this is L, this is U. So this is 1, 1, 0. This is 1, 2, and this is 0. So I want to do minus 2 row 1 plus row 2. So simply this is 2. So minus 2 plus 2, minus 4 plus 8. So this is 4. So 1, 2 comes here, and then this is 2 here, and 4 plus 4 is 8 here. Okay. And this I can write as 1, 0, 2, 1, L. D is 1, 0, 0, 4. This is D. This is L. And this one is simply, so when I take out 1 from here, this will be still 1 and 2. And when I take out 4 from here, this is 0 and 1. This is same as U is L transpose. So these two matrices are same. So when we have symmetric matrices, so for symmetric matrices, when matrices work with half the matrix, which means what? Which simply means if A equals ABC, B, D, E, C, E, F, if I do minus B over A row 2, row 1, minus B over A row 1, minus B over A row 1 plus row 2, I should get A, B, C. This goes to 0. This becomes D minus B square over A. D minus B square over A. This becomes E minus BC over A. E minus BC over A. Maybe I write this one as B square over A too. b square over a, and when I do minus c over a row 1 plus row 3, this is 0. This is e minus bc over a, e minus bc over a, and this is f minus c square over a, f minus c. So these are the same. These are the same. So, and actually no need to store. This implies no need to store both L and U. This is all we want to do from chapter 1. I've already assigned the end problems for chapter 1, which are actually almost all the problems at the end of the chapter. It's a good exercise if you try to attempt all of them, and if you get stuck somewhere, and then do send me an email, or do send Dr. Babri an email, and we'll be happy to help you out. Thank you very much, and next time we'll start with chapter 2.